Morning, one and all. Welcome back to the video lecture series. This is Dr. P.C. Noslu, Probability Theory Stochastic Process. Today, we are going to discuss about time average of random process. Now, suppose if we take a signal x of t, how to calculate average value? 1 by t integral 0 to t x of t into dt. It is the average value of any signal, nothing but DC value calculation. Now, instead of signal, we are considering here it is a random process. So that random process also is a function of time. So for our convenience, this previous discussion, we have shown corresponding f of x comma t like that. But if it is like a signal, so this random process also I am writing like x of t. Now, what is the difference between the time average function? Average function means usually it is strictly limited to a certain period, 1 by t integral 0 to t, or 1 by t integral minus t by t to plus t by t. There is no extra. Here, the time average function formula, if you see it, again x bar means average and mean value. It is equal to a of x of t. Here the symbol a indicates average value, time average value of random process. Time average value of random process. Generally, it is a general average. You can write the expected value of x of t. Generally, we are going to write expected value of x of t. Here, the main difference we need to notice here, the expected value of x of t is general average. Now, for time average, we are going to write a into x of t. Now, what is the difference? We have a little bit of confusion. What is the difference? Again, entire formula is same. There also, we are going to write 0 to 1 by t, 0 to t, x of t into dt. Extra here, we are going to consider that limit t tends to infinity, 1 by 2t, that interval is from minus t to plus t. Suppose if you write from 0 to t, write from 0 to t, 1 by t. If you write from minus t to plus t, it is 1 by 2t. So limit t tends to infinity, 1 by 2t, integral minus t to plus t, x of t into dt. So it is the time average of random process. Next, time autocorrelation function. Already we know autocorrelation function. That is a Rxx of tau. Rxx of tau is equal to Rxx of t1 comma t2 is equal to expected value of x of t into x of t plus tau. It is equal to, whenever it is Rxx of tau, it is independent of time, then we can say that is a void and stationary random process. So the same concept here, the time autocorrelation function. There, for autocorrelation function, generally general Rxx of tau is represented. Now, for showing the difference here, that R is not going to be represented a thick R. It is going to be represented here a 2 times of scaling R. So we are showing the difference between time average autocorrelation function, general autocorrelation function. In general autocorrelation function, we have represented with thick R, the symbol. Here it is a thin R. So this, again, if you observe here, Rxx of tau, there it is a expected value. Here we are representing a average value, x of t into x of t plus 2. Now, if you want to write in formula like average, similarly, we can write limit t tends to infinity, 1 by 2t, integral minus t to plus t. Instead of x of t, here we are going to write x of t into x of t plus tau into dt. Okay. So that is the only difference between general autocorrelation and time average autocorrelation. Now coming for a time cross correlation function. A cross correlation means autocorrelation means within the same random process. So we are going to consider it at two different time instants. That is the thing. When we are coming for a cross correlation, we are going to consider two random processes. One is x of t, another one is y of t. So for this, if you write the formula, rxy of tau is equal to 1 by 2t, limit t tends to infinity, 1 by 2t, integral minus t2 plus t, x of t into y of t plus tau into dt. So it is not always, it is not t plus tau. You can also write t minus tau, no issue. Because it is, we are going to be delayed or going to be advanced. But finally, it must be the difference between the two time intervals. X of t, t plus tau minus t, or t minus tau minus t, like that. So that is the intention of here. So it is equal to rxy of tau. So the difference is in the general correlation, cross correlation, there is no any one limit t tends to infinity. Generally, we are going to write. So that is the ensemble difference between ensemble average, this time average of average value and autocorrelation and cross correlation. Now, within the again in the time cross correlation function also, you need to satisfy the properties whenever this expected value of a into x of t, expected value of a into x of t, it is nothing but expected value of x of t. You see this expected value of x of t, random process always remember, there is a random variable we are going to represent capital X. Whenever it is a function of time, it is going to be called random process. Expected value of x of t is a average value, general average value. So here, whenever it is a time average, we are representing a into x of t. That is the difference between a into x of t and e into x of t. E into x of t means general average value. A into x of t means time average value. So here in this case, whether it is a time average or general average, both are same. So expected value of this a into x of t, nothing but x of t, x bar, both are same. Next, you see the second one comparison. Expected value of a into x of t into x of t plus tau means it is a autocorrelation. Time average autocorrelation, expected value, nothing but general autocorrelation. So we need to show here this expected value of rxx of tau means time average autocorrelation function is same as general autocorrelation function. Similarly, you can also write for expected value of rx by tau means the cross correlation. The cross correlation also it is a same. So while we're calculating time average function and time autocorrelation function, time cross correlation function, whenever if we calculate expected value of time average function, time autocorrelation function, time cross correlation function, it is equal to your general expected value of x of t, expected autocorrelation function and cross correlation function. So that is the main basic concept. Next, if you see this ergodic theorem and ergodic process, we observe here the difference between small x bar and capital X bar. This small x bar indicates time average function, time average value. Capital X bar means general average value. So, if this is the condition, the ergodic theorem states that a random process x of t, all time average sample function of x of t are equal to the corresponding statistical average of x of t. Statistical average of x of t means what? A general average value we are calculating expected value of x of t. Now this time average means we are representing as A into X of t. So whenever these two are same, that is called ergodic theorem or ergodic process. So here we are writing this expected value of X of t is equal to time average value of X of t, and corresponding autocorrelation function, general autocorrelation function, time autocorrelation function. So autocorrelation function and time autocorrelation function both are same, then it satisfies the ergodic theorem or ergodic process. Now you see general jointly ergodic process. Jointly ergodic process means we need to consider two, like cross correlation. X of t is one signal, y of t is another random process. So here we need to check individually. X bar, small x bar is equal to capital X bar, small y bar is equal to capital Y bar. What is the small x bar? It is the time average of random process. What is the capital X bar? General statistical average. Now individually you can check Rxx of tau is equal to, Rxx means it is a time average autocorrelation, time autocorrelation function. Rxx of tau means general statistical autocorrelation. Next, Rxy, time autocorrelation. It is statistical autocorrelation. Ryy, time autocorrelation. Ryy of tau, it is a statistical auto. So the difference is time means we are going to consider in the formula limit t tends to infinity. So these are all are equal, then we can say it is a jointly ergodic process. Jointly ergodic process. Now again it is a mean ergodic process, autocorrelation ergodic process. Already we discussed the same concept here. So next one is properties of autocorrelation function. So we know the autocorrelation function means we have considered the signal random process x of t, and then we are going to be test at two different time instants. So whenever if we calculate this autocorrelation function within the same random process at a different time instants, it is a not function of time, it is a independent of time. Whether it is independent of time or it is a dependent of time. Suppose it is independent of time, we can say it is a void and stationary process. Suppose it is a depends on time, it is not a stationary process. So all the time we are going to test whether it is a void and stationary or general random process. So first one, in the autocorrelation, if you want to calculate mean square value of x of t, mean square value of x of t. Mean value you know. What is the mean value? Integral 0 to 1 by t, integral 0 to t, x of t dt. Square means we need to get x square. So in the autocorrelation formula, what is the autocorrelation formula? Rxx of tau is equal to expected value of x of t into x of t plus tau. So in the whenever if we substitute tau is equal to 0, we are going to get expected value of x square of t. So expected value of x square of t nothing but 1 by t integral 0 to t x square into x square t dt. Okay, so we will see this. We observe this one. Rxy of tau is equal to Rxx of tau is equal to expected value of x of t into x of t plus tau. So whenever if we substitute here tau is equal to 0, it is a expected value of x square t. So this expected value of x square t, how we are going to write in the formula? Instead of x of t, we are going to get here x square of t. Okay, so simply you can write 1 by t integral 0 to t, whatever we have a this x of t instead of x of t, we are going to write this is x square of t. Okay, x square of t into dt. It is about mean square value, or whenever if you substitute tau is equal to 0, usually it is going to get a maximum value. Compare with the remaining all tau values whenever it is tau is increases from from 0 to infinity or from 0 to minus infinity, remaining all values of tau, that corresponding correlation value is going to be less compared with the whatever the value of tau is equal to 0. So we will see in the next class about this. I'm going to stop.